We all have must have learned about the maximum power transfer theorem in our basic electronics course. But if we calculate the efficiency at the maximum power transfer theorem, the condition that is the load resistance should be equals to the source resistance, we get an efficiency of 50%. And intuitively thinking, it might not make sense. Mathematically it's correct and it should be correct, but intuitively it doesn't make sense. So we will see what does it really mean and the correct way to look at it. Now, if let's start with the maximum power transfer theorem statement. It states that the maximum power is transferred from source to the load. That means the power that is being consumed by the load is maximum only when the load resistance is equals to the source resistance. And the source resistance, by this I mean the Thevenin's resistance. The source is modeled as a modeled in its Thevenin's equivalent. Now let's do a small experiment. By changing the load resistance from very small value to a very large value, what do we get? First, keeping the load resistance to a very small value, that is essentially short circuiting it, what do we get? We have the least amount of resistance present in here. So the maximum amount of any extra resistance, the load resistance will cause extra resistance, which will eventually decrease the current flowing through the circuit. So at when the load resistance is 0, the maximum amount of current will flow. And whilst we essentially only consider the power being consumed at the load side only. So our only consideration is the power that is being consumed by the load. And because the load resistance is 0, we know by the power consumed power formula, it is I square R, and the R is 0, hence the power is 0. So the power starts from here. Let's also look a bit about this graph. On the y-axis we have the power consumed, the load power, and this x-axis is the ratio of the load resistance to the source resistance. And when the load resistance is 0, the ratio is 0, and hence we get this point. Now we increase the load resistance to the maximum value, that is essentially open circuiting the whole circuit. So the current flowing through the circuit will be minimal, or we can say that the I flowing through is approximately 0, will be very small value. And when we do that, the I square term will drop even further. So we can say that the load power is I square R. I square being very small, we can consider it as 0. So the load power will go to 0. And if we extend this circuit, we will get the curve going like this. If I have to draw a smooth curve, it will be like this. Okay, so we will have some maxima, and it will eventually drop to 0 at both ends. So this is the load resistance value, this is the power consumed. Now this maxima, as the theorem states, is occurred when the load resistance is equals to the source resistance. And this is actually okay, let's go down here to get a good picture. So the useful power which we are seeing is the load resistance. So if we consider something as an electric machine or some amplifier, we will see the load resistance or the useful power being modeled as some load, and the source resistance, the losses such as the armature resistance losses, the field resistance losses. I'm talking in consideration to electrical machines, so it can be applicable to any circuit in general. So the load power, which the useful power is being taken through the load, and the losses, the source resistance, the Thevenin's resistance, is just a modeling for the internal losses. Okay, so the useful power is I square RL, and the losses are I square RTH, the Thevenin's resistance, or I square RS. You can write any of it. So the maximum power transfer at that condition, we are only looking at the absolute value of the power. We are not considering the efficiency or the point of maximum efficiency. We are only considering the absolute value of power that is being consumed by the load. So by the above analysis, we can clearly state that the power consumed by the load will drop to 0 at both the ends, and will attain a maxima where the source resistance is equals to the, or the load resistance is equals to the source resistance. RS being equals to RL is not the same as RL being equals to RS. Here in this case, we are considering RS to be variable, but in this but actually the RL is variable, and also it's a important thing to consider while studying this theorem, that we are considering only the load resistance to be variable, and we are keeping the source resistance and the source voltage constant, because it's just a modeling of whatever the source is being available to us. Okay, and if we calculate the efficiency, in we know efficiency is given by output power plus losses. Okay, so the output power is I square RL, the losses are I square RS, and simplifying this, we get this expression. Now this expression actually tells us something more about the circuit. So let's conduct the same experiment as we did in the above circuit, above thing. Okay, so let's repeat the same experiment. When we keep the load resistance as small, like keeping it very small. Okay, so the numerator is very small, approaching to 0, and the denominator is some. If we neglect if it is very small, we can eventually approximate the denominator to RTH. So very small value upon anything will give you a very small value. Okay, now what did we get when we had RL to be very small, approaching to 0? We had efficiency approaching to 0. We will talk about the physical significance, and like we will intuitively analyze the circuit, but let's now just analyze through the mathematical way. And if we increase the load resistance to a very large value, so we have a very large value on the numerator, let's write it as RL, and we have a very large value of RL here in the denominator, and compared to it the source resistance is very small, so we can approximate the denominator to RL, and from this we get 1 represents 100%, or the maximum efficiency that can be attained by a circuit. Now let's analyze the circuit intuitively. What happens when we keep the load resistance? See, we are only talking about load resistance because that's the only thing variable here. So as you increase the load resistance, the voltage drop across, from the voltage divider principle, the voltage drop across the load resistance increases, and as the voltage drop increases, the power consumed by it increases, because it is eventually V square upon R. So V increases, R and R, as RL also increases, it increases in a square, so it is proportional to RL. So the efficiency is proportional to RL, by which we can state that as we keep on increasing the load resistance, the efficiency will decrease. Mind you, we are not talking about the power that is being consumed, and the power analysis is actually being done by the maximum power transfer theorem. So if we want the maximum power to be given to the load, we have to keep the load resistance equal to the source resistance, which will give us the maximum absolute value. We can uh, um, suppose 20 watts, 30 watts, like this. And if we want the maximum efficiency, it will decrease the power, like if we keep on increasing load resistance, the current will also decrease. Okay, when the current decreases, the losses also decrease, giving the maximum amount of power. The power that is actually being drawn from the source, the most of it is being consumed by the load. So we have a very good graph here. So similar to the above thing, we have this which represents the load power, and we have this graph, the black graph, which represents the efficiency. We can see that the efficiency keeps on increasing and asymptotically reaches 1 or 100% as RL upon the ratio of RL to the source resistance, the load resistance, the source resistance goes to infinity. Okay, and the load power reaches a maximum value when the load and the source resistance are equal. And I hope this clears a bit of like the confusion. And yeah, thank you.